question is, what can we do with these exponential functions, and yeah, what kind of problems could we run into? So here's one. It says find a formula for an exponential function passing through the points -2, 6 and 2, 1. Okay, so if we were to graph this in some way, we would have -2, here's 2, 1, 2, 3, 4, 5, 6. Okay, so we'd have something like this, and then 2 1s over here. And the thing is, okay, how do you connect those 2 points when we're not given an a, right? No vertical intercept or initial value. So how do we work with this? So let's just write. I always like to start off problems by writing down the applicable or appropriate formulas. Okay, so we're just going to write down this 1 plus r to the x, and just in case we need it, we can write down this alternate form as well. Okay, so in this case, what we're going to do is say, okay, so these 2 points, what's really going on is we have -2, 6. This is our x value, right? And then this is our y value, our f value. So we have x, when x is equal to -2, our f of -2 is equal to 6. Okay? So what we can do with this information is plug it in to one of these formulas, right? And in this case, I'm going to pick this formula here, because it's just simpler to work with a b instead of having to move around this 1 plus r everywhere. Okay, so let me show you how we're going to do this. So f of -2 is equal to a, because we don't know that, b, because we don't know that, and x we said was -2, right? That's the input we're plugging in, and we know that this value is equal to 6, because that's what they told us, right? That's what this point gives us. When we plug in x, and when we plug in -2 for x, we get out a 6. Okay, so we're going to look at this, okay, and then, okay, we're kind of at a standstill because we don't know a, we don't know b, etc., but we do have another piece of information. We're given the point 2, 1. So let's set up a similar equation, but with this point instead. So now this x is 2 and y is 1, so 1 is equal to f of 2, right? That's what that means. And then if we just plug that in, we get a times b to the 2 power, to the +2. Okay, so now we have this other equation, and the 1, I'm just moving that over again to the other side. Okay, so now we have this equation 2 to work with. Okay, so we have this one here, as well as this one there. Okay, and when we have 2 equations with 2 unknowns, it's called a system of equations. And you can actually have more variables and more equations. But just in general, the name for this is a system of equations. So basically what we can do now is solve for a and b, and I'll show you how to on the next slide. Okay, so we're at the following. We have 6 is equal to ab to the -2 power, and then we have 1 is equal to ab squared. Okay, so what we're going to do is we're going to take one of the equations, let's say this one, okay? We're going to solve for one of the variables, and by solve I just mean get it by itself on its own side of the equal sign. So let's say we solve for a, okay? So what we're going to do is multiply times b squared on both sides, b squared. So then these exponents cancel out, and we just get 1. Okay, so a is equal to 6 times b squared. And what was the point in doing that? Why did I want to get a by itself? So that we could substitute this side in for the a over here on this equation, on this secondary equation, okay? So what I'm going to do is just take all of this, which is equal to a, and I'm going to plug it in for the a spot. Okay, so now we have 1 is equal to 6b squared, okay, and then times the b squared that was already there. Okay, so see how we kind of reduce this problem to a single variable problem or equation, right? So now it's easier to work with, and we know how to solve for b here. So then this is 6b to the 4th. If we divide by 6 on both sides, we get b to the 4th is equal to 1 over 6. And then we take the 4th root, which is kind of strange, but if you have a calculator, it's not that big of a deal, right? So then we have this, which when you do plug it into your calculator, we get something about 0.6389. Okay, so we solved for b, and now what we're going to do is just plug it back into here in order to figure out what is our a. Okay, so in order to figure out a, we just have a is equal to 6 times whatever b is, so 0.6389, and then that's squared, right? And then when we do that, again into our calculator, we get something around 2.4492. Okay, so now we've gotten to a point where we know our b, okay, and we know our a, so we can just plug it into the formula to get our answer. So now we have f of x is equal to a times b to the x. So a is 2.4492 times b, which is 0.6389, 8, 9, and then raised to the x power, okay? And that is the function, or that is the formula for the exponential function, which goes through those 2 points given in the beginning. So for the examples that we've done so far, and the problems we've worked through, the change, or the rate of change, the percent rate of change has been applied every year, right? Because we said, okay, John has blah, blah, blah amount, and then his grandpa and his mom and whatever, they're going to somehow change that total by whatever, 15% or negative 50% each year, okay? So the thing is, sometimes the time interval between changes, or between changes that occur in your total occurs, and that interval is shorter than 1 year. And what do I mean by that? So now we're going to explore the topic of compound interest. Okay? Compound interest. So this is when, let me write it down explicitly here. So time between changes in total occur more, well, not occur more, sorry, is shorter than, there we go, because I'm saying that the time in between your changes is shorter than simply 1 year. Okay, and this also works for the case of 1 year as well. This is just a more general formula for how to calculate how to model exponential functions. Okay, so what do I mean by this whole statement here? So what I mean by this is that sometimes you'll see a problem when it says something is compounded, you could say annually, and that would mean then your time interval is going to be 1 year. So then we're back at the original problem that we had, like the original formula, right, that we've already explored. We could also have semi-annually. That would mean twice a year. Okay, we could have quarterly, etc., monthly, etc., etc., etc. Okay, so the formula, the general formula for this, is going to be slightly different than the one that we had before. Okay, and I'm just going to denote it like this: A of t is equal to A times 1 plus r. So it looks pretty similar right now, but here's the change. So now we're going to divide r by k, and then raise that whole thing to the kt. Okay, so the only thing that we really introduced here, the only thing that's new is our k. All right, so the only new change, or addition, we could say, the new variable that we introduced here is this k thing, right? So what is k? K represents the number of compounding, just some definitions here, periods in 1 year. In 1 year. So let's explore this concept of k some more on the next slide. Alright, so this k thing, okay? So this, like I said, it's the number of compounding periods in 1 year. So what does that mean in plain English? This just means how many times per year the percent change is being applied, okay? So let's look at some examples of what we could get for k. So for example, if we said annually, okay, and these are like the trigger words. So annually would mean that k is equal to 1, okay, because you only apply the change once, like once per year, right, annually. So then we had semi-annually, okay, and then this would imply that your k is then 2, okay? What about quarterly? You have 4 quarters in a year, so presumably, so then k is equal to 4. If you had monthly, for example, with that keyword, we assume that k is equal to 12, because you apply it once a month, the change. So, and you have 12 months in a year, so k is equal to 12. We could also go weekly if you really want to. Usually they only ask up to monthly. But anyway, so k would then equal to 52 or something like that. And you can go on and on. Alrighty? So now let me rewrite the formula here for compound interest. So we have A of t is equal to A times 1 plus r over k, and then raised to the kt power. So in this context, what is r over k? So r over k, so r itself is the annual percent rate. Okay, so this means like per year, how much is what is our percent rate of change? Okay, so annual percentage rate per year. okay? And k is the number of times per year that you're compounding. Times per year. So ultimately this whole thing, the like over year cancels out, and we just have that it isn't annual anymore, but this is the new percentage rate for one compounding period. For one compounding period. So what do I mean by this? This is pretty confusing stuff, but basically what you're going to do is take this entire rate for the whole year, divided by the number of times you're going to be compounding during that year, such as like 12, let's say, okay? And so if it were monthly, you would take your normal annual R and then divide it by 12 to see per month what are we increasing our rate by, okay? Or what is our rate? Okay, so that's what R over K is. Alrighty, so this is the new percentage rate for one compounding period, whether it be a month, a week, or a quarter. Okay, and now let's explore what's happening with this KT thing. What does that represent? Okay, so here what we have is K represents, again, number of times you compound per year. Okay, and T is just our number of years. Okay, number of years. So ultimately the years cancel out, and we just have, okay, so how many times are we going to be compounding? Okay, given a number of years. Number of times we compound, or apply the change. Compound. Okay? Alrighty, so let's look at some examples. Alrighty, so we have, if we invest $3,000 in an investment account paying 3% interest compounded quarterly, how much will the account be worth in 10 years? Okay, so again, let's write our formula down and then try to identify what we can label our information as, what variables we can stick them under. Okay, so this is our entire formula for compound interest. Alrighty, so it says if you invest $3,000, so that means our initial amount, our lowercase a, is going to be $3,000. Okay, and then we have, as we read along, an investment account paying 3% interest, so that's going to be our rate. R is equal to 0.03. That's 3% written as a decimal. Compounded quarterly, okay, so that signals us to make our K equal to 4, right? Because we're going to compound 1 time per quarter, which means 4 times per year, right? And then it also says how much will the account be worth in 10 years, okay? And T is measured in years, so T is equal to 10. Alrighty, so let's just set up our general formula without plugging in T equals 10 yet. Okay, so A of T is equal to 3,000, okay, times 1 plus 0.03 over K, and that's a 4. And then up here we just have a 4T, okay? Alrighty, so once we do that, then we can just plug in our 10 for T. So A of 10, this will give us the amount we have, or how much the account is worth in 10 years. Right, so this is going to be equal to 3,000 times 1 plus 0.03 over 4 times 4, to the 4 times 10 power. Okay, so when you plug this into a calculator, we get something that's around the amount of $4,045.05. So this is about how much the account's going to be worth in 10 years. Okay, and it's really important to understand what each of these variables means. The A, that's our initial amount. R is the annual percent rate of change. Okay, so per year. K is the amount of times you compound in 1 year. And T is the amount of years you're actually doing it for. Okay? Satisfaction.